Hi, welcome everyone to session 14. In this session, we will discuss about decision trees for classification. So decision trees are one of the most important techniques or algorithms for solving classification problems. They can also be used for regression, and they are probably the most widely used technique or algorithm in businesses. And there are specific reasons for it. We will explore that in this particular session. So let's get started. Like all sessions, I have created, for this session, I have created a folder called session 14 in the GitHub location. And I've uploaded these two files, the Python notebook for decision tree and the data set called hr.scp.csv. So let's upload and to the Jupyter notebook. And this is classification using decision trees. For this, we'll be working on this data set called HR attrition, in which we'll build a model to predict if an employee will leave or not leave an organization based on specific attributes or characteristics of an employee. And we have taken the data set from the Kaggle. There is a variable called left, which is 0. If the value is 0, means the employee did not leave, and 1 means the employee has left the company. And we'll try to predict that based on certain attributes, information about the employee that has been captured, like satisfaction level, last evaluation, number of projects he or she has worked on, what's average monthly hours, and so on and so forth. We have gone and dived in detail about this data set and done EDA on this data set in the previous session, in session 12. And if you're not familiar with data set, I recommend that you go and look at session 12 and 13 first before coming to the session 14. So let's go ahead and load the data set, import all the libraries required, and then read the CSV file. And let's look at few samples. So here you can see this employee satisfaction level is 0.63. Satisfaction level varies from 0 to 1. And last evaluation also varies from 0 to 1. And this employee has not left the organization. So 0 means not left, 1 means left. And let's look at how many data points we have. We have about 14,999 samples. And this is a very clean data set because I have chosen this data set primarily to focus on discussing the algorithm here, how to apply the algorithm. And we have total 10 columns, and out of that, 1 is the outcome variable left, and remaining 9 are the independent variables, the X features. So let's do a specific EDA where we will create a scatter plot between satisfaction level and last evaluation. I've chosen only very few samples to explain this concept. And we'll separate them on the basis of left and not left. So I've taken the variable hue as a left. So if you see here in this particular plot, the X values are satisfaction level, which varies from 0.0 to 1.0. And the last evaluation also varies from 0.20 to 1.0. And the orange dots means the employee has left, and the blue ones means the employee have not left. So if you look at these values, mostly the employees which are less satisfied, probably the value is less than 0.4 or something, they have left, and more than 0.4, they have not left. Of course, there are also some employees who were not very satisfied with these blue dots. They're still not left, they're in the company, not satisfied. And there are employees who are very satisfied, this orange dots. The satisfaction level is very high, more than 0.8, and still they have left. So now, what decision tree does it here? It kind of creates a decision boundaries or decision rules. So decision rules or boundaries based on their feature values. For example, the value of satisfaction level, whether it is a 0.2 or 0.3 or 0.4. And these are threshold values to create partitions that maximizes the separation of different classes, which means it tries to find out how to create this decision boundaries. For example, what happens if I take satisfaction level is a less than 0.2 as a decision boundary, if it's less than, people mostly left, and if it is not less than 2, people have not left. So is this a correct decision boundary? Does it separate the two different classes the most optimal way, which maximizes two different classes? Or the decision, like if the satisfaction level is less than 0.4 is a better decision boundary, or satisfaction level is 0.8 is a better decision boundary. So it tries to find out, or it searches for the optimal decision boundaries based on the feature values. Not only on the satisfaction level, it also does the same thing for your last evaluation. It tries to find out decision boundaries, which separates these classes, the not lefts from the lefts. But as you can see, there probably won't be decision boundaries. For example, if I choose a decision boundary here, it will not create a decision boundary where you can separate the two different classes, where each group, this partition, contains only people who have left, and this partition contains only people who have not left. The pure separation probably is not possible, because this is a reality, right? And but it maximizes that partition. But how do we know that? How do we understand that? So that is based on the decision tree splits the data based on features that provides the most information gain. This is probably one of the important concepts in decision trees, called information gain, or a reduction in impurity. Impurity estimation is a concept used in decision tree classification models to measure the homogeneity or the impurity of a set. What is homogeneity and impurity of a set? Let's understand that first. And it is given by, of course, ultimately you have to measure through a particular matrix or index. So there are two possible metrics here. One is called Gini impurity, and the other one is called entropy. So let's understand that first. What is impurity? How to measure it? And how to measure homogeneity? And how this particular matrix actually helps you to measure that. So Gini stands for 1 minus pi square, summation of pi square. So let's look at one simple example. Let's say I have two sets here. Set 1 and set 2. So in the set 1, let's say I have only the samples that belongs to one class. Let's say I denote the left class here as positive and not left classes as a negative sign. So let's say in one set, I have samples where everybody has left. So when I create partitions, let's say one partition Okay, everybody has left one set, and the other set, let's say, half of them have left and half of them have not left. So as you can see, there is an absolute homogeneity here. That means there is no impurity at all. But here, half of them have left and half of them have not left. That means the impurity is maximum. Because if you just randomly take a sample from here, it could be 0.5 for left and 0.5 for not left. But if you randomly take a sample from here, the plus ones will be 1 and the negatives will be 0. So let's calculate the Gini for this. So the Gini here is summation of 1 minus summation of pi square. So that is 1 minus. What is the probability of being positive here? That's 1 square. What's the probability of being 0 here? That is 0 square. So 1 minus 1 becomes 0. So when the Gini value is 0, that means there is absolute homogeneity, no impurity at all. But if you look at this particular set, 1 minus, again, summation of pi square will be 1 minus the probability of finding positives. Here's 0.5, so that's 0.5 square. And the probability of finding negatives is again 0.5 square. So that comes out to be 0.25 and 0.25. If you add them, 0.5. So 1 minus of that is 0.5. That means the Gini value here is 0.5. The Gini value varies from 0.0 to 0.5. The Gini value, they always vary from 0.0 to 0.5. And 0.0 means no impurity, absolute homogeneity. And 0.5 means completely random. The impurity is highest. Now it tries to know so the objective of decision tree is to find the boundaries where the Gini is minimized, minimum Gini. Like any other model where we try to minimize the error, here tries to figure out the decision boundaries, which creates the maximizes the partition across two different classes, means the Gini is minimum. It can also be done through something called entropy, but let's look at Gini first. Definition: it measures the probability of misclassifying a randomly chosen element in the data set if it were randomly labeled according to the class distribution. A lower Gini impurity indicates a more homogeneous node. Similarly, entropy, it calculates the level of disorderness. This is a concept comes from physics, or uncertainty in a set of samples. Entropy is maximum where all class levels are equally probable, that means highest disorder, and decreases as the distribution becomes more skewed. Again, the goal is to minimize here the entropy. So in this case also, if you look at in the two sets where in one set everything is positive, so the probability of being positive is 1 and the probability is negative being 0.0, vis-a-vis the other set where the probability of being positive is 0.5 and being negative is 0.5, let's say. The two different sets. And if you calculate the entropy here, it'll be minus, let's say, 1, log of 1. Log of 1 is 0. So minus 1 minus the other class, 1 minus 0, log of, again, 1 minus 0. So log of 1 is 0, so that becomes, it becomes 0. The whole equation reduces to 0. That means the entropy is again 0. Means there is absolutely no impurity or disorderness in this particular set. But whereas in this case, it will be minus plus are 0.5 and minus are 0.5. So it will be like minus 0.5 log of 0.5 base 2, which will be equal to 0.25. I'll just look at that. So minus again 1 minus 0.5 plus log of 1 minus 0.5. So both the equations reduces to same thing again, 0.5 log of 0.5. So let's look at what is a log of 0.5. You can say import numpy as np and minus 0.5 log of n multiplied by np dot log 0.5 base 2. So let's look at maybe math function values. Math function. .5. So this value becomes 0.5. And this value also becomes 0.5 plus, right? Because I've taken the negative symbol here. So that becomes 1.0. So entropy value varies from 0.0 to 1.0. And 0.0 means there is absolutely no disorderness, and 1.0 means there's a maximum disorderness. And either whether you use Gini or entropy to create decision boundaries, the objective is always try to minimize the Gini or entropy. So now let's look at a couple of decision boundaries in detail. So Gini impurity ranges from 0 to 0.5, like we already discussed. 0.0 represents a perfectly pure node. All samples belong to the same class. And 0.5 Gini value indicates maximum impurity. Samples are evenly distributed across different classes. So 0.5 for one class and 0.5 for the other class. Now, let's look at first how much total impurity is there. There's a concept of total impurity. So without decision, what is total impurity in this particular mix? So here there are 20 samples total, and out of that 1, 2, 3, 4, 5, 6, 7. So 7 are left and remaining 13 are not left. So if you look at the total impurity in the complete mix would be 1 minus 7 divided by 20. That's left the probability square, and 13 divided by 20 square. So 1 minus PA square. And if you do this, the total Gini would be 0.0455. So this is the total Gini that is there. And now if we apply a decision boundary rule, and when we separate the classes, okay, now this particular decision rule or boundary should have reduced that to 0.455. Okay, but how much it reduces, we will look at. So now let's say if the decision rule is satisfaction level less than 0.2, so this will look something like this. So if we apply this particular decision boundary, and you can see if satisfaction level, if satisfaction level is less than 0.2. So now on the left, there are only people who have left. There are 2, but on the right, there are remaining 18 samples. Out of that, 5 people have left and remaining 13 have not left. Okay. So what is the Gini on the left? So this is Gini on the left, Gini 1. That will be 1 minus 2 out of 2 square and 0 out of 2, because there is no people who have not left. So this is because this is a pure node. So of course the Gini value will be 0. The other side, the Gini would be 1 minus of 5 out of 18 square minus 13 out of 18 square. Okay, so this will be the 0.040. So when we and the total impurity in the mix is 0.455. And when we divide it by if or separated by this condition called satisfaction level is less than 0.2, the left node had an impurity of 0.0. It's a completely pure node. And this one had a 0.40. Now, how much of this Gini, this is of course on the both the nodes. So how much of Gini totally reduced? So that's basically called information gain. So how do we calculate that information gain? So information gain is a concept used in decision tree to measure the reduction of entropy or impurity, in this case, Gini, achieved by splitting the data based on a specific attribute. Because now the difference is we calculate the 0.455 impurity based on 20 samples. And when we split the data on the left node, the impurity is 0.0. And we had only 2 samples here. And we have 18 samples and the impurity was 0.40. Okay. So you have to calculate the total impurity weighted by the number of samples here. So this is 2 samples, 18 samples here. So we calculate the weighted Gini here. So that will be on the total node will be the actual Gini based on the fraction of the samples. So we have 0.0 on the left, and total number of samples are 2 out of 20 plus 0.40 multiplied by 18 by 20, because total we have 20 samples, right? So this will be the total Gini at the child node. And then what we do is, then we subtract the total impurity without separation and after separation. So let's look at the total Gini at the child node. That comes out with 0.361 now. So 2.2 divided by 20, this is 0. 18 by 20, this will be 0.40. That's why we got here. And the total impurity after separation at the child nodes are 0.36. So difference should be now 0.45 and 0.36. So we have reduced the total impurity from 0.45 to 0.36. So that comes out to be 0.09. So total information that we have gained, or total reduction in the entropy or impurity by applying this particular decision boundary or criteria, is 0.09. We have definitely, so this decision criteria definitely helped us in separation, and the reduction is about 0.09. But the problem is this the best that we can do? Or is there a better decision criteria which reduces this Gini even further? Right? So let's look at another decision rule. Let's say we get a decision rule here, a boundary here at 0.45, right? So now if you look at it, on the left node, there are mostly people who have left, of course, a couple of people who have not left. And here again, most people who have not left and a couple of people who have left. But is this the better splitting criteria? We can now calculate the Gini on the left, which would be total number of samples here, 1, 2, 3, 4, 5, 6, 7. So 5 out of 7 have left and 2 out of 7 have not left. So that would be the Gini would be 0.040. And on the right, so 2 out of 13 have left and 11 out of 13 have not left. So it comes out to 0.26. And now what we'll do is we will do a weighted calculation, because there are 7 samples here and 13 samples here. So 7 divided by 20, 13 divided by 20, and their corresponding Ginis. All right. And if you look at that now, it says the information gain is 0.14. That means if we apply this particular decision criteria, that satisfaction level is 0.45 instead of 0.2, which reduces the Gini by 0.09. This new criteria 0.45 reduces the information by reduces the Gini impurity by 0.14. So there is more information gain here. So we can conclude that this particular decision tree criteria, satisfaction level is less than 0.45, is definitely better than satisfaction level 0.02. So what decision tree does it? It does an extensive search, okay, based on the possible values for the decision criteria, and checks which particular criteria gives the maximum information gain, okay, or reduces the Gini or reduces the impurity mostly. Okay. And that is chosen as the best splitting criteria. And it does it not only on the satisfaction level, right? Now it also creates, for example, it creates saying the satisfaction level is less than 0.45, gives a Gini, reduction in Gini is 0.14, or information gain, right? It gives information gain 0.14. Similarly, it creates splitting criteria based on the last evaluation. And let's say in the last evaluation, less than 0.8, I'm just taking an example here. The information gain is maximum is 0.11. Okay. So it does extensive search across all the features, satisfaction level, last evaluation, number of projects, average monthly hours, everything, except left, of course, this is Y value. And then finds out across all features which splitting criteria gives the best information gain or a maximum reduction in the impurity. And that is chosen as the top node for a decision tree. Now, what is a top node for decision tree? Now, let's look at the decision tree itself. So this is an example of a decision tree. We will create this plot by end of this particular session. So decision trees can also be visualized. That's one of the biggest benefits of this particular algorithm. So if you look at here, this, of course, the whole thing looks like a tree here. And this is the root node. This is the second node. This is the third, fourth, and fifth. So there are 5 different criteria, the hierarchical conditions they created, right? And these are basically called depths. So this particular tree has the depth of, so this is 1, this is 2, this is 3, this is 4, this is 5. And this is no condition here. This is basically the groups created by the last condition. So this tree has a depth of 5. And the first node, the root node, the condition that the criteria that is chosen is satisfaction level less than 0.465, because this criteria would have given the maximum information gain. The decision tree algorithm does it, the searches across all features would have figured out saying that this particular criteria gives a maximum information gain. And if this particular condition satisfies, then this is the yes and this is no. That means all the employees who have less than 0.465 satisfaction falls in this group now, and who are more than 0.465 falls into this group now. So this particular group that we see here, this particular group of people who have a satisfaction level less than 0.465, and this group is more than 0.465. And this group contains the total number of samples. As you remember, there are 11,999, the training samples. Now, if you apply this particular criteria, this gets further divided into 3,314 samples here, and the remaining 8,685 samples here. So there are 3,314 employees who have satisfaction level less than this, and the remaining who have more than this. And if you look at the decision tree, applies conditions and segregates the data into smaller segments. For example, this is the first condition, if satisfaction level is less than 0.465. Then if the employee has worked on number of projects less than 0.25, this is yes. So this is also yes. And if the last evaluation is less than 0.575, yes. Right? So after applying all the three conditions, so here there are about 1,266 employees are there. That means if the employees satisfaction level is less than 0.465, and if number of projects worked is less than 2.5, and if this is less than equal to all are, and last evaluation is less than equal to 0.575. And then there are about 1,266 employees are there in the data. And out of that, if you see, out of that, 75 have not left. Only 75. And remaining 1,191 people have left. That means in future, anybody who satisfies these three criteria, the probability of him leaving is pretty much 1191 divided by 1266. A very, very high probability. Right. Same thing, if the satisfaction is less than 0.465, yes. And number of projects worked on is less than 0.25, but the last evaluation is more than 0.575, no. So this satisfied them. That means more than 0.575. Then there are about 105 employees are there. Out of that, 99 have not left, and only 6 have left. So if you look at the decision tree, all the blue boxes belong to the majority belong to the left classes, and all this orange one belong to the not left classes. And overall, also one important information is you look at the Gini at the top, which is 0.36. Now, how this Gini would have been calculated? This is the total Gini in the complete training sample. Because in the total training sample, 11,999 samples are there. Out of that, 9,100 have not left. The first one is always not left. The second one is left. So the Gini would have been 1 minus summation of 9178 divided by 11,999 square plus summation. So 2821 divided by 11999 square. So I leave it to you to calculate this, and this should have actually come to 0.36. And it shows us this criteria which divides the group into 2 separate classes. So the weighted Gini of these 2 groups would have definitely be lesser than 0.36. And one thing you can observe, as we divide the data by different conditions and go down, and you can see at the bottom, the Ginis are coming down to like 0.0, 0.043, 0.0, 0.198. And you can see all these conditions are helping you to segregate the data and create smaller groups or smaller homogeneous groups. That means it's able to segregate or divide the data or partition the data into smaller groups, which are either left classes or not left classes. Right? So you can apply these rules. And once this tree has been created, all that you need to do is to decide if a new employee or an existing employee will leave the organization or not. Then you basically take all the information and drop it here. And based on the condition, right, you can see ultimately the employee falls into which bucket at the end. Let's say the employee falls into this particular bucket, right? And then you can say the employee is not likely to leave, because previously in the historical data, we have observed employees with a similar, the same criteria mostly have not left. That's why this employee will also not likely to leave. Okay, so this is the beauty of this particular algorithm, which gives you the conditions in not in mathematical form, but a rule-based if else conditions. And businesses love this algorithm because they can actually read this, what the algorithm says, why this employee is likely to leave or not likely to leave. What are the different conditions which are highly interpretable, right? So decision trees have a multiple different benefits or advantages. One of the advantages, of course, because of this boundaries, many different boundaries, it can encompass non-linear relationships, which can capture non-linear relationships between the independent variables and the dependent variable. Second one is the model is highly interpretable because it generates if and else conditions, and which can be read through. And there are, of course, it can also be visualized. So it's very important to visualize a model, again, from the interpretability perspective. And there are, of course, a couple of more advantages. We'll look at that as we go ahead. So what we'll do now is we'll actually build the complete model, because we have only kind of understood it from a couple of features and how this is done. So let's do a model by taking all the features. But I've also given a participant exercise here. So you can also calculate the information gain for the decision rules, right? Using the last evaluation. So two criteria, 0.55 and 0.85. So and you can see which of these rules gives you the maximum information gain, and which you can calculate based on either Gini or Entropy. So that gives you a good understanding of how this decision criteria are being created. So now let's look at the data set now. So we have two categorical features, as we have observed here, department and salary. We need to be, they need to be encoded into one hot encoding format. So let's first create the dummy variables for them. Get dummies, HRDF, columns, department and salary. And once you encode them, we can see the numerical features are as they are. Okay. Though work accident and promotion are also categorical in nature, but they have already been encoded into 0 and 1. So we'll continue with that. But the remaining ones, like a salary and departments, have been 0, 1 encoded now. Now let's build a decision tree, set X and Y values. So all the X features, the X features would be all the columns in this particular data frame now that we have obtained from this HR encoded after encoding the variables, except left. So remove the left from the X features. So these will be my X features now. All these numerical features. And the new 100 encoded features. And we'll create X and Y, HR encoded DF X features, and Y will be left. Let's first split the data into train and test. We'll again use the train test split. We'll test the data into 20 and 80. That means the train size will be 80% and test size will be 20%. And X train is now 11,999 samples and X test is 3,000 samples. So we have total 14,999 samples. So this is 80% of the data and this is 20% of the data. And let's build a decision tree first. Scikit-learn tree. So the tree models, there are multiple different tree models are there. We'll come back to this, explore them in the future sessions. So you can import decision tree classifier. Similarly, there's a decision tree regressor also there, which can help you to solve regression problems also. So it's very important that you import the appropriate classifier here, the decision tree classifier. And then we will initialize the model here. So here we have to specify these two parameters. What criteria you want to use, Gini or entropy. So in this case, let's choose Gini. You could have chosen entropy also. And what is the depth of the tree that you want to create? For example, here, if you see, we created a depth of 5. But you can also create more or less depth. We'll explore about how to choose the right depth in the future session. But for the timing, let's hard code this as a depth 5. Okay, and first create the tree and understand that. And later we'll explore what is the right depth. So these two parameters are called hyperparameters. So there are models where there are no hyperparameters. For example, linear regression or a logistic regression, we did not use any parameter. But decision tree, we can actually use these parameters. And these parameters can be tuned so that you can find the optimal value. Whether it's a 5 or 10 or 15, you can find the optimal value, which gives the best accuracy. And the whole process of finding the optimal value for hyperparameter, it's called hyperparameter tuning, which we have explored in the KNN also, found the number of neighbors is a hyperparameter tuning. Right? But in this case, we'll just simply explore one decision tree. So we'll hard code it to 5 and Gini and see that. And then we'll fit the training data, X train and Y train. So now the tree has been built. Now we'll go and validate what accuracy this gives on the test data. So predict on the test data, tree predict X test. And if you look at the samples now, we'll create data frame like we did last time. We'll create data frame with 2 columns, the actual value and the predicted value by the tree. And you can see this is a correct classification. This correct class. In fact, most of them are correct classifications here, but we could have gotten some misclassifications also. This is, of course, randomly sampled data. So we'll go and look at what's the total accuracy that we are getting. Y test and Y pred. The total accuracy comes out to be 0.975, which is almost like 98% accurate. And if you remember the same data set, when we used logistic regression, of course, we used only one variable. We came out to be 0.76 or something. But this is 0.98. So this is actually an extremely wonderful module. But then total accuracy does not give you the complete picture. As we discussed in the session 13, we'll look at the confusion matrix and look at specific attributes of that matrix. Scikit-learn confusion matrix and confusion matrix display. We'll create the confusion matrix and create the display. So here, if you look at the confusion matrix, now these are the actual labels and the columns are predicted labels. So this is your true positive. So this is true positive. This is false positive. The false negative and true negative. So my recall value is very high, looks like now. So recall value would be, so if you remember the recall value, it's a true positive divided by true positive plus false negative. So how many actually left? There are about 757 people who have left. Out of that, how many we were able to correctly identify? 703. Only 47 people could not be identified by the model. So that's a recall value. And the precision is how many the model told they are going to leave. And out of that, how many actually leave. So the precision here would be 7 TP divided by TP plus FP. That's a precision. So you can calculate all this. Like we saw last time, there are different specific methods are there. Precision score, recall score, F1 score. The classification report gives you all the details. So let's look at the classification report. And for the class 1, the recall score comes out with 0.94. So which is 703 divided by 703 plus 47 comes out with 0.94. And 703 divided by 703 plus 27 comes out with 0.96. So that's a precision and that's a recall score. And that's a F1, which is 2 times precision of recall divided by precision plus recall. So in this case, like we already discussed in the previous session, the false negatives are important to minimize because they are very costly for this particular model. And we'll take the recall score as a matrix to understand if the model is good or not. The recall comes to 0.94, which is a pretty good score, which means if I have to explain a simple language, that if there are 100 people who are likely to leave, okay, this model can identify 94 of them. Only 6 people will go undetected. We can detect 94 of them, only 6 people will go undetected by the model. So which itself shows that model is a quite good model. You can also measure ROC and AUC. We've gone through ROC, AUC. So we'll go calculate the probabilities, the predicted probabilities. So here we simply predicted the 0 and 1s. And we we did this with the decision with the probability threshold of 0.5. So if the probability of y is more than 0.5, then y equal to 1 left, and less than 0.5, y equal to 0. This is the assumption here. But here we look at the actual probability values. And if I print them also, let's say y df dot sample 10, and we can see we get the probability values here, right? And based on that, we'll create the ROC AUC. Let's look at the ROC AUC score. ROC AUC score also comes out with 0.9, which is pretty good. And this is the ROC AUC curve, right? Which is very close to reaching this particular point, 0.1 here, right? Because 0.98. So this is a pretty good model. It's able to, the ROC AUC score 0.98 means the model's ability to distinguish or discriminate between the left classes from the not left classes is extremely good, right? So decision tree are sometimes they gives very better results, but anyway, you have to look at the data and try both all models and see which gives the better result. So in this case, decision tree gives you much better result. Now you can visualize the tree also, like I told you. To visualize a tree, there is a function called plot tree, which can be used. So plot tree, the tree model that we have created here. The tree model. We have to pass tree model, and then we pass all the information, like what are the feature names, what are the class names. Otherwise, it's going to show 0 and 1, which is not interpretable. So you have to give the proper class names. Fill true is basically going to color code them. So left classes are blue and the not left classes are orange, and then the font size. So let's import plot tree first, and you can see the tree has been created, and you can save it. You can also load it later, display image, and this is the tree that has been created, which we already gone through and discussed. So this is the beauty of this algorithm, that we can create a tree, we can also interpret it, and you can also visualize it. The other most important feature or benefit of decision tree, it also measures the feature importance. Now, what is feature importance? Feature importance is, now all these features in the decision tree, right? For example, satisfaction level, number of projects, average monthly hours, right? They help reducing the Gini, or they help gaining information gain, right? But each of these features would not have contributed towards information gain equally. Some would have reduced the Gini, or increase in information gain is better than the other features. That's why satisfaction level has been chosen as the most important feature here in the top node, because it helped, compared to other features, it helped to reduce the Gini maximum, right? And then probably other features have been chosen as the second best feature and third best feature, and so on and so forth. So what it does is, it keeps track of how much of information gain is contributed by all these features across all these conditions and criteria in the whole decision tree. And then it converts that into a feature importance, and it gives you a feature importance of each variable. And let's say we take that feature importance and put that into a data frame with the feature name and the corresponding importances. And if you sort the value by the importance, let's print that. And you can see each feature's importance level is given here. And this is primarily based on what is the contribution, right, of that particular feature towards reduction in Gini or information gain. Right, and all these importances are relative importance. And if you add the importance of all the features, the summation of all the importances will be equal to 1.0. So they are relative importance, and you can see here, this particular feature satisfaction level is 0.52. That means, in a way, you can interpret this as the amount of information that satisfaction level has to classify this data into two different classes, like left and not left. Okay, that is half of the information, 0.52. So this is a very, very important feature. Next to that is time spent in the company. How many years the employee is there in the company. Then last evaluation, number of projects, average monthly hours. And if you see, the remaining features are pretty much very close to 0. That means there are absolutely no contribution of these features in separating the classes from left and not left. Not even salary. That could be the reason because most of this information would be probably already embedded into the satisfaction level. So in the presence of this feature seems to be redundant. Okay, it's not necessary. So you can actually go and build a model with only these 5 or 6 features. 1, 2, 3, 4, 5 features. And this will also give you almost 90.97 or 0.98 accuracy. Okay, I'll leave that as an exercise for you, participant exercise. Now you can create another column called cumulative importance. That means top 2 features, how much important, top 3 features, and so on and so forth. So there's a function called cumulative sum. You can do that, and you can see the first feature is 0.52, of course, but this is the summation of these 2, and this is the summation of these 3, and so on and so forth. And you can see by the time we reach the 5 features, right, this is almost 0.999, close to, right? So all the information that is there are required to classify between left and not left. 100%, almost 100% information is there within this 5 features. And you can actually go and build a model. And this is, that's why decision tree is also used as a feature selection technique. So in a model, if you have a, let's say, 40, 50 or 100 features, and you want to understand which features are most important, then you can actually build a decision tree. Of course, the tree model itself has to have better accuracy, then only can rely on these importances. The first you look at how accurate, how good accurate the model is, and then you can come to the importance and look at it. And you can sort them by the importance. And let's say you have to select only 10 features, then you can select the top 10 features. And this also gives a benefit, saying that when you deploy the model, right, if you only know this 5 pieces of information for each employee, you will be able to classify them whether they are going to leave or not going to leave. You don't need to collect all in other information, like which department he or she is working on, what is the salary bracket in which he or she is. All these informations are not necessary. So that's it brings us to the end of this particular session on decision tree. I've given you 2 different exercises here. One is to build a decision tree here with a combination of these 2 different criteria, like max depth is 10 with Gini and max depth is 5 with entropy. So you can actually use these hyperparameters and measure the ROC AUC of the model and see if you can further increase the 0.97 even further, right? And build decision tree with the top 5 features, like I told you, based on the feature importance, and find the accuracy matrix like ROC, AUC, and confusion matrix. So these 2 exercises, along with the exercise here that I've given here, to find the Gini based on last evaluation, will definitely give you a very good understanding of how decision trees work. And in the next session, we'll dive deeper into a little bit of hyperparameter tuning, overfitting, underfitting, all these concepts. So let's end the session with a quick recap of benefits of decision tree. The decision trees offer several benefits over other machine learning models, including interpretability and easy to understand. This is, I think, one of the most important criteria why businesses widely use this model. Handling non-linear relationship between variables, and gives you the feature importance, which helps you to also select features. So enabling feature selection and dimensionality reduction. And of course, you can also visualize the tree, which is not possible with any other models, but that's of course linked to the interpretability and easy to understand. So making it easier to explain and models predictions to the stakeholders, okay, which is an important criteria when you solve a very high risk models, right? Important, and the models are important for business decision making. So thank you, and please complete the exercises and share them in the Discord group if you want. And see you in the next session with a new topic. Thank you.